Hi everyone. So in this video we are going to look at the Claussius Clapeyron equation. In the previous video we looked at the Clapeyron equation. We derived the Clapeyron equation. In this one we're going to start from the Clapeyron equation and derive this kind of related equation, which is the Claussius Clapeyron equation. Right, so the Clapeyron equation, to remind you, the Clapeyron equation that we found was, so it's the slope of the coexistence line on the phase diagram. dp dt is equal to qt. Right? This is the latent heat of our phase transformation divided by the temperature at which the phase transformation occurs times the change in volume. And so if I sketch a phase diagram, we have temperature on the x-axis, pressure on the y-axis, and then we might have something that looks kind of like this, where over here we have the solid phase, in here we have the liquid phase, and then over here we have the gas phase. Right? So this is kind of a and in here we have our triple point. Over here we have our critical point. So this is just a fairly typical phase diagram, solid, liquid, gas phase diagram. And now the Clapeyron equation then applies at any point on any of these coexistence lines, right? So we can sort of apply it to some point here, and it's going to tell us about the slope of our coexistence lines. Let me just draw this one with a little bit more curvature. Right, so if we applied the Clapeyron equation here, then it tells us about the slope of the coexistence line at this point. And we looked at two examples, and we saw that this can be very useful, right? But when we tried to apply it to do a calculation for how much the boiling temperature of water changes with a large pressure, we found that we didn't get a very good result. And that's because you can see that the slope is also changing as a function of temperature, right? So really what we would need to do is to integrate the equation. So we could write down dp, right? So just sort of rearrange this equation. dp is equal to qt t delta v dt. And actually, let me give myself a little bit more space. So dp, right? And so what we could do is integrate both sides, right? So we integrate from P1 to P2, and we integrate from T1 to T2, and then we could get a better estimate for the for how the pressure is changing with temperature along the coexistence line. But in order to do that, then we need to know, whether these other quantities, Q and delta V in particular, whether they also depend on the temperature. And that's why the Claussius Clapeyron equation, the Clapeyron equation itself applies for any of the phase transitions. The Claussius Clapeyron equation is specifically referring only to the liquid gas phase transition, right? So we're specifically only referring to this phase transition here. So let's do that then. So what we need to do is to look at this quantity delta V, right? And so delta V for the liquid gas phase transition is going to be the volume of the gas minus the volume of the liquid, right? But we know that the gas state has got a much greater volume than the liquid state, right? So we can say that this is the delta V is actually approximately equal to the volume of the gas. And then if we also then assume that in the gas state, if we use the ideal gas equation, then we can write down that delta V is equal to RT over P, right? So this is we're making sort of two approximations here. One that we're assuming that the gas volume is much greater than the liquid volume, and then the other one we're assuming that the gas behaves as an ideal gas. Right? So two approximations, but these turns out these will work pretty well. And then we are going to assume that the latent heat of vaporization. Okay, because up here I've got QT, so this is latent heat of some transformation, but for the Claussius Clapeyron equation we're talking specifically about the liquid to gas transformation. And so we're saying that, so we have then the latent heat of vaporization, and we're saying that this doesn't vary with temperature, right? So we assume the latent heat of vaporization does not vary with temperature. And this turns out to be a fairly good approximation. Right? And so with these two things, then we can now perform our integration. Right? So let's let me just write this out. So the dP dt we had equal, so it's the latent heat of vaporization divided by the temperature times the change in volume, and with the substitution of delta V from above, then this is going to be the latent heat of vaporization divided by temperature times pressure divided by the gas constant times the temperature. So if we rearrange that, we'll have 1 over the pressure times dP is equal to the latent heat of vaporization divided by the gas constant. And remember, we're assuming the latent heat of vaporization doesn't depend on temperature, and times 1 over T squared dt. Now we can do our integral. So we have the integral from P1 to P2 of P minus 1 dP is equal to the latent heat of vaporization divided by the gas constant times the integral from T1 to T2 of T to the minus 2 dt. And this then is equal to the natural logarithm of P evaluated from P1 to P2 is equal to the latent heat of vaporization divided by the gas constant times minus T minus 1 evaluated at T1 and T2. And so then we can see that this is going to be the logarithm of P2 minus the logarithm of P1, which is equal to the latent heat of vaporization divided by R times minus 1 over T2 minus 1 over T1. And then, we use the property of the logarithm that log P2 minus log P1 is equal to log P2 over P1. So we have the natural logarithm of P2 divided by P1 is equal to the latent heat of vaporization divided by the gas constant R times 1 over T1 minus 1 over T2. And this then is our Claussius Clapeyron equation. And so again, just to re-emphasize, the Claussius Clapeyron equation applies only to the liquid gas phase coexistence line, and to be clear, we have made several approximations in deriving this expression, but these approximations turn out to work fairly well, and we used this expression to calculate an example. So we looked again at this example of water boiling on Mount Everest, and we got a result that was pretty close to the experimentally measured value.